Welcome back to The Explainer. Today, we're diving into an absolute game changer. We're looking at a leap in modern engineering that literally changed the course of human history. We're going to explore the architecture of the Intel 8085 microprocessor. But, instead of just thinking about it as a cold, dead piece of hardware, I want you to picture it as a silicon brain. It's got memory, it makes logical decisions, it talks to the outside world, the whole shebang. And we're going to unpack exactly how it pulls all of that off. So how do you teach a piece of silicon to think? It's kind of a mind-blowing question, right? Well, to really appreciate the answer, we have to rewind a bit. Back in the late 1960s, computers were absolute behemoths. I'm talking massive processors built using thousands of separate, discrete elements just wired together. They took up entire rooms, they chugged ridiculous amounts of power, and honestly, compared to what we have today, they were agonizingly slow. But then, boom, the microchip revolution of the 1970s hit. Engineers actually figured out how to condense all those scattered, room-sized components onto a single, tiny piece of silicon. And just like that, the microprocessor was born.
So, here's our roadmap for this explainer. We're going to build this complex concept piece by piece. We'll start with what is a microprocessor. Then we'll cover the architecture of the 8085, map out the communication highways, decode the language of machines, and finally, wrap it up with instructions and execution.
Okay, let's dive right into our first topic. What is a microprocessor? Fundamentally, a microprocessor is just a programmable device. It takes in numbers, performs arithmetic or logical operations based on a program stored in its memory, and then spits out a result. But here's the catch. This silicon brain, it has an incredibly narrow view of life. It doesn't understand letters or colors or sounds, nothing like that. It strictly understands binary numbers, zeros and ones. Each individual 0 or 1 is called a bit, and the processor crunches these bits together in specific groups called words. For the 8085, its word size is exactly 8 bits. Now, to put the sheer genius of 1970s engineering into perspective, get a load of this number. 6,200. The Intel 8085 is a single-chip NMOS device packing 6,200 transistors, and operating at a 3 MHz clock frequency. Those 6,200 tiny microscopic switches are orchestrating literally every single piece of math and logic the chip performs. For its time, it was an absolute marvel. Now that we've nailed down the definition, let's move on to part 2, architecture of the 8085. When you map out a high-level layout of a microprocessor-based system with the microprocessor sitting right in the center, you can easily spot its 3 core internal organs. First up, there's the arithmetic logic unit, or the ALU. This is basically the calculator. It's where all the heavy lifting, the actual data processing and math goes down. Next is the control unit. You can think of this guy as the traffic cop, coordinating the timing and the flow of data across the whole system. And finally, we have the register array, which acts as the CPU's internal, super-fast storage, holding on to the numbers that are actively being worked on right in the moment.
If we zoom a bit deeper into that register array, we find the microprocessor's specific internal scratch pads. Right at the very top is the accumulator, simply labeled A. Now, this 8-bit register is super special because almost all ALU operations revolve around it. It holds one of the operands right before the math happens, and then bam, it stores the result immediately after. Down below that, you have your general-purpose 8-bit registers, labeled B through L, and fun fact, these can actually be paired up if you ever need to handle larger 16-bit operations. Down at the very bottom, we've got 2 dedicated 16-bit registers, the stack pointer and the program counter. Those 2 are absolutely essential for keeping track of memory addresses.
Now, what's really fascinating here is the flag register. While all those other registers are busy holding raw data, the flag register holds context. It's an 8-bit register, but the individual bits inside it act as physical indicators, or flags, that alert the system about the status of whatever math operation the ALU just finished. Let's quickly break down these 5 status flags. The carry flag trips if a math operation results in a carryover, kind of like when you do long addition on paper. The 0 flag, as you might guess, lights up if the result of an operation is exactly 0. But really think about the sign flag. This single bit gives the processor absolutely critical context. If the bit is a 1, the result sitting in the accumulator is negative. If it's a 0, the result is positive. These simple little flags are exactly how the processor knows how to react and make logical decisions within its programming.
All right, we've seen the internal organs, so let's step outside to part 3, the communication highways.
The 8085 connects to the outside world using a system of wires called buses. It's basically its nervous system. First, we have the address bus. This one uses 16 lines. Because it has 16 bits, it can generate 2 to the power of 16 distinct combinations. What does that mean for us? It means this tiny chip can directly pinpoint and access up to 65,536 different memory locations, which equals 64 kilobytes of memory. Once it locates a specific memory address, it then uses the 8-bit data bus to actually ferry the data back and forth. But here's the question, how does the memory actually know if the processor wants to send data or receive it? Well, that is handled by the control lines. There's a specific read signal and a write signal. Plus, there's a vital IO/M signal, which basically tells the entire system whether the processor is trying to talk to an input-output device, like a keyboard, or if it's trying to talk directly to its internal memory. It keeps everyone on the same page.
Now we need to shift our focus from the physical wiring to the actual vocabulary we use to speak to this silicon brain. Let's look at part 4, the language of machines.
When you're programming at this bare metal level, you're really dealing with two different languages. Machine language is the raw, pure hexadecimal or binary code. This is exactly what the microprocessor directly reads and executes. But let's be real, us humans are terrible at reading endless strings of ones and zeros. So instead, we use assembly language. This uses human-readable mnemonics, which a handy program called an assembler then translates into that raw machine code for us. Although it is super important to note that these languages are completely dependent on the specific hardware. You literally cannot take 8085 assembly language and just run it on a totally different chip. It won't know what to do with it.
A perfect example brilliantly illustrates how that translation works. The 8085 uses 246 unique bit patterns to form 74 distinct instructions. So imagine the binary pattern 0011, 1100. In hexadecimal, that translates to 3C. When the processor reads that highly specific hex code, it immediately recognizes the instruction INRA, which stands for Increment Accumulator. By feeding it that exact, specific pattern of ones and zeros, you are triggering a very precise physical action inside the processor's ALU, telling it to add the number 1 to whatever value is currently just sitting in the accumulator. All right, let's bring all of these concepts together by tracing the actual journey of an instruction from start to finish. Part 5, Instructions and Execution. This process is the absolute heartbeat of computer science, the fetch-execute cycle. First, your program is just resting quietly on the memory bookshelf. The microprocessor reaches out over the address bus and fetches an instruction, bringing it inside via the data bus. Then, the instruction gets decoded, and the ALU actually performs the requested mathematical or logical operation. Finally, if it needs to, the newly generated result is written back out to memory. And it does this over and over and over, millions of times every single second.
So the crucial point here is that for this cycle to actually work, almost every single instruction needs to be broken down into two distinct parts. First is the opcode, or operation code. This tells the machine exactly what task to perform, like adding or moving something. Second is the operand. This is the actual data that the operation will be performed on. Because honestly, knowing what action to take is completely useless if the chip doesn't know what data to take it on, right?
Every single one of the 74 instructions the 8085 knows falls neatly into one of these 5 groups. Arithmetic and logic instructions handle all your math and Boolean operations. Branch instructions actually change the flow of execution, which allows the program to jump around instead of just reading in a straight, boring line. Machine control handles the base CPU operations like halting everything, but pay close attention to data transfer with commands like movie or MVI. These simply copy data from a source to a destination. The data in the original source is never deleted or changed by a transfer command. It is strictly a copy and paste operation.
Finally, decoding all these opcodes, accessing the operands, and moving the data around, well, it doesn't just happen randomly. It relies on a strictly choreographed rhythm. The timing and control unit generates 7 basic timing cycles, like the opcode fetch cycle or the memory read cycle. Every single operation the microprocessor performs is meticulously paced to these internal clock cycles. It's honestly like a symphony of electrical pulses, just keeping total, perfect order in the system. So we've seen how the 8085 works, from its internal registers right down to its assembly language. And when you sit back and really look at it, it is astonishing. This little device used just 6,200 tiny transistors to process 8 bits of data at a time. Yet it sparked a revolution that completely reshaped human communication, business, and science forever. Today, our modern processors have tens of billions of transistors etched onto a single chip. So I'll leave you with this thought. If that early, incredibly simple architecture fundamentally changed the world in the 1970s, what are the ultimate limits of the silicon brains powering our future? Thanks for joining me on this explainer. Keep wondering and keep learning.